Okay, so we are still discussing functions of two or more than two variables, independent variables. So last time we already looked at the limit and at the definition of continuous, which then once we have defined the limit will naturally follow from the limit definition. We also extended these definitions already to functions of three variables. Of course, you can extend them further to functions of more than three variables, but then things are maybe more complicated to write down unless you use vector notation, which is then more suitable. So we will define, like, if you have a function. Okay, now the x, we look at it as a vector. Okay, it can be a vector in the n-dimensional vector space. So maybe x has n coordinates. And for such functions, so this is a better notation than for functions of arbitrary many independent variables. For such functions, we again define the limit. Where x tends to some vector a, so we say that this is equal to some L a real number. And what we mean by this is, okay, so we have the usual epsilon delta definition. So for all epsilon larger than 0, there exists a delta which might depend on epsilon, such that, and if we use vector notation, things look pretty similar to how they looked like last semester. So for all x, we have for all x, if the distance of x and a is larger than 0 and smaller than delta. But of course, here we have a different distance. We have the usual distance for two vectors, the Euclidean distance. So for all those x, we have that the function value will be close to L, will be within an epsilon distance of L. So this is the usual definition for the limit. And once we have this definition, we can define continuous. So f is called continuous. At x is equal to a, some vector. If so, just the usual definition. If we can obtain the limit just by plugging in the a. Okay, and we saw last time already that for if we go from one dimension, so from the case we have discussed last semester, if we go to two or more dimensions, the evaluation of limits can be slightly more tricky. But essentially, we have many of the laws, or all of the laws which we have proved or we have used last semester are true here as well. So you have that, for instance, the sum, the limit of a sum is the sum of the limits, and all those laws you're used to. Also, but disproving here that the limit relation holds, you can essentially use one of the approaches we have used last semester, which was to show that the left-hand limit and the right-hand limit both exist but are different. But here you have much more directions, which can make it sometimes more complicated. So we saw last time many examples. For instance, let's maybe do one more example, which is for the general n-dimensional case. So for instance, if you consider this function f of x, where x is a vector, is equal to the length of x, then from last semester you would guess that this function should be continuous for all x. And of course, this is easy to prove. In this case, you can even use the epsilon delta definition in order to prove it. You just have to observe. So what we have to prove is, so our claim is that for every vector, the limit of this function is obtained just by plugging in. Okay, so we have to prove that, okay, if I give you an epsilon, you have to give me the delta such that if the distance between x and a is smaller than delta, the distance between f of x and the claimed limit, which is the Euclidean, which is the length of a smaller than epsilon. But this is quite easy here because if you plot this situation here, so if we have here an x and here we have an a, then this vector will be the difference. Okay, so you know from simple geometry that the length of this vector squared will be equal to the length of a squared plus the length of x squared minus twice the length of a times the length of x times the cosine of the angle which is between those two, where theta is this angle here. Okay, so but the cosine of theta is always smaller or equal than 1. So what you get is, okay, this is larger or equal than the absolute the length of a minus the length of x, everything squared. Okay, so you get an inequality, or maybe I write this here. You get an inequality which is this one, so the length of x minus a will be larger or equal than the length of x minus the length of a. This is the, sorry, this is not the length, this is the absolute value of the length of x minus the length of a. And this is essentially what you need, because you see now, if I give you the epsilon, okay, then you will choose the delta equal to epsilon, okay? Because then for the vectors where the length between x and x minus a is smaller than delta, okay, you will have that this is satisfied. Okay, so from this we already get, so we get that by choosing delta is equal to epsilon, we get the claim. Okay, so the only thing you have to show here is this inequality here. This is one way to prove it, but there are certainly different ways, and this shows that that this function here is continuous everywhere, directly by using the definition of the limit. Okay. So any questions? Okay, so we have now the notation of limits, and we have the notation of continuous functions. Now the next step is to look at the notation of differentiability. And this will turn out to be not more complicated as in the one-dimensional case, but maybe a little bit unusual if you see it for the first time. So the definition will be rather more complicated than, would be slightly more complicated than than for functions of one variables. Now, before we try to understand, okay, what does it mean that the function of, for instance, two variables is differentiable? Okay, we look at something which is related, namely partial derivatives. Okay, so we have given, again, a function of two variables. So we start always with a function of two variables and then move on to the higher dimensional case, should be said. So we have given a function of two variables. Okay, so what we can look at is the following. So we have given some points a, b. Okay, we look at the function which is defined as g of x is equal to. So we plug for the second coordinate, we plug in b and just look at the function as a function of the first variable. And here we can use the usual derivative. Okay, so if we use the usual derivative at a point a, then by the definition last semester this is just the limit. Then h tends to 0, and then we have f of a plus h b minus f of ab over h. Okay, so we just take, and This means we just take the derivative with respect to the first variable, and we assume that the second is a constant. Okay, and this kind of derivative is called partial derivative. So this is called, we use the notation. This is the partial derivative of f of x at ab. Okay, so this is the definition of the partial derivative with respect to x, and the definition of the partial derivative with respect to y is similar. Just everything for the second coordinate. Now this is one way to denote this. Another way to denote this is we write the x here as an index. Also this we will frequently do. Here we write the y as an index. Sometimes we also write here 1 for the first, because it's the partial derivative is with respect to the first variable. Here 2 because it's with respect to the second variable. Okay, so this is a certain derivative for this function here. Two of them. We still, of course, we have to interpret what is the meaning here of, for instance, this number here. But this is rather easy because you see that what you do here is you look at this function here. So this function will give you some surface. If you plot the graph, you will have some surface. And we fix a point AB. So we have then here the corresponding point on the surface where the x and y coordinates are AB. Now what we do here is y is equal to b. So this is a plane which is parallel to the xz plane and which is passing through this point here. So we look at the cross sections. We look at the cross section with the plane which is passing through this point here, and this will give us a curve. And this curve actually described by this equation here. Okay, and the slope of this curve at the point P, okay, is this partial derivative here. And similar, if you look at the cross section which is not parallel to the xz plane but parallel to the yz plane, then you will get this curve here, C2. So this is C1, and you can interpret this as the I mean, maybe I should say this is the point P. So you can interpret this as the tangent slope of the tangent to C2 at P. Okay, so both of them, you can interpret them as certain slopes of the cross sections obtained by slicing the surface with planes which are parallel to the xz plane or parallel to the yz plane and pass through a given point. Okay, and the point has coordinates AB and f of AB. Okay, so these are certain. You can interpret them as certain slopes. Of course, you can also interpret them as a rate of change, where you assume, for instance, for this one, you assume that the y is constant, okay, equal to b, and this will give you the rate of change now with respect to x at x is equal to a. Okay, so you have both of these interpretation you have for these partial derivatives. The reason why we define this we will understand later on, because essentially our goal is to find the notation for differentiability of such a function. Okay, and maybe I should say already now that we will not define such a function to be differentiable if and only if those two exist. This will not be our notation of the differentiability. Okay, so we will, of course, one way you could say, okay, if you want to define what does it mean that such a function is differentiable, okay, you can say one way is, okay, I define, okay, those two exist. Then I say this function is differentiable. We will see this is not a very good, this is not, such a notation of differentiability, okay, will not have the properties we expect from a function to be differentiable. Okay, so the differentiable will be defined different So these are rather two quantities which are related to properties of this curve here. Okay, namely, once more, this gives you the slope of the tangent to C1 at the point P, and this is the slope of the tangent to C2 at the point P. Okay. Let's look at an easy example. For instance, this one. Okay. So here, if we are asked to compute the partial derivative first with respect to x, so this means that y is a constant. You can look at y as a constant. Okay. You take the derivative. So you interpret this as a function of x. So the derivative becomes y x to the y minus 1. Or if you compute the partial derivative with respect to y, okay, now x is the constant, so this is like a function like 2 to the x. So in this case, you have x to the y ln x. Okay, and you can interpret them once more as either as rate of change if you keep one of the variables fixed, or you can interpret them as the slope of the cross sections at the point x, y, z. Another example, for instance, would be this one. So also this is a function of two variables. Okay, and it's not complicated here to compute also the partial derivative. So the partial derivative with respect to, let's say first to y. Here x is a constant, so I just have to take the derivative here. And what I'm going to use is the fundamental theorem of calculus. So what I get then is this here. If I want to compute partial derivative with respect to x, now what I have to do is, okay, this is the partial derivative of, I have to change upper and lower limit. Then I get a minus, so minus y to x cosine of t squared dt. And now again, by the fundamental theorem of calculus, so y is a constant, minus cosine of x squared. Okay, so this is already the answer. Okay, so you see it's pretty easy. You just have to be careful which one is the one you keep constant, and which one is the one you're going to take the derivative. But essentially, this is very trivial. And of course, we have something also. We can also use the method of implicit differentiation here. So if you have a function of two variables which is implicitly given, then you can use this method to find the derivative. Now, how about functions of more than two variables? Functions of three variables. Of course, for such functions, you can define partial derivatives as well. Of three variables. Then, for instance, the partial derivative with respect to x at some point a, b, c is defined as the limit. Now h tends to 0, and you have f of a plus h, b, c minus f of a, b, c over h. So similar definition, and similar for the other partial derivatives. So with respect to y, you always keep two of them constant, or two of them do not change, and one of them is then you take the derivative with respect to this variable, and then you plug in y is equal to p. And here, of course, and similar for the partial derivative with respect to z, here, of course, you do not have any interpretation as a tangent anymore, because you here we are now in the four-dimensional space, but you still can interpret these kind of quantities as rates of changes. So for instance, this will give you, okay, you keep the y and z constant, and this will describe you, okay, how does the function behave or change if you look at different values of x. So this is then the rate of change of the function, instantaneous rate of change of the function at x is equal to a. So you still have this kind of interpretation, and this kind of interpretation still shows you in some way that these quantities will be important and will to some extent describe some of the properties of the original function. And you can do the same for functions of more than just three variables. Then you have something like here. Okay, so the partial derivative of f with respect to some xi is then defined as the limit. Again, h tends to 0, and then you have f of x1, and you go on. So all of them are constants. Only xi at the i's coordinate you have xi plus h, xi plus 1, and you go on until xn. And then you have minus f of x1 up to xn, and everything divided by h. So, and this is then called the partial derivative of f with respect to xi. Okay, now the next thing. I guess you have encountered things like this already in other classes, so I don't have to do any examples. Anyway, this is just doing examples is just the usual. You just use the usual rules for differentiation, and just keep in mind that two of the, for instance, for functions of three variables, two of the variables are considered to be constant, and you take just the derivative with respect to the remaining one. So this should be quite easy. Of course, once we have defined the partial derivative with respect to x and with respect to y, for instance, the partial derivative with respect to x itself is a function of two variables, so we can again consider partial derivatives, which are so-called higher derivatives. So we can define we have the partial derivative, for instance, with respect to x, of the partial derivative of the function with respect to x. For this, we also use this symbol. Or for short, we write this as by this symbol here. Now, similar, we can take the partial derivative now with respect to y of the partial derivative of z with respect to x. Okay, so here we will write f of xy, and we have also this symbol, so we will write this here. Here, the partial derivative with respect to y, partial derivative with respect to x. You have to be careful here because of the order. Okay, so here, if I use this symbol, okay, this means first with respect to x, then with respect to y. But here I write it the other way around. So here I have to read it from here to here. Okay, so this is first with respect to x. So I have to look here. This is the first one. This is the second one. Okay, whereas here it's reversed. Okay, so don't be confused by this. Now, and the same for the partial derivatives with respect to y. So we have here f first with respect to y and then with respect to x. And again, we will write this as the partial derivative, second partial derivative of z with respect to first y and then x. Here, but here written in the other way around, and we have the partial derivative of the partial derivative with respect to y. Now, once again with respect to y. So this is f y, and this will be written by this here. So we have for a function of two variables, we have 4 second-order partial derivatives. And of course, you can go on and also define higher derivatives, where you take, for instance, this one, and then again compute the partial derivative with respect to x or with respect to y and so on. So you can go on like this. But of course, for us, it remains to interpret these quantities here, okay, or to demonstrate that they are useful. Let's maybe look at an example. Okay, so you see that the partial derivative with respect to x is what? For this, you have to use the product rule. So you have y e to the x plus xy e to the x. Now the partial derivative with respect to y. Okay, so it's x e to the x. Now for the second partial derivatives. For the second partial derivative, both times with respect to x. So we have to take now here the partial derivative with respect to x. So we have y e to the x. And here we again the chain rule. So plus y e to the x. So this is twice plus and then x y e to the x. Now the second partial derivative first with respect to x, then with respect to y. Okay, so we have to take this one now with respect to y. Okay, so we have e to the x plus, and here we have x e to the x. Now the second partial derivative first with respect to y and then with respect to x. Okay, so we have to take this one now with respect to x. So this one is e to the x plus x e to the x, and the second partial derivative both times with respect to y, okay, is equal to 0 because this does not depend on y anymore. Okay, so you see for this example, those two are the same. And this is not a coincidence. For many, many examples, those two, no matter, if you choose many, many different examples, you will see it looks like always, those two are always the same. They are not really always the same. So you can find functions where they are different. But indeed, for most of the functions, those two partial derivatives, sometimes called the mixed partial derivatives, will be the same. And this is so-called Clause's theorem. So Clause's theorem tells you under which conditions are the two mixed partial derivatives the same. Okay, so you need assumptions for this, as I said. So what we assume is assume that the function is defined in some domain, let's say disk. Okay, so assume that f is defined on a disk with, let's call it disk D with A, B, and D. Now, what we need as assumptions is that the partial derivatives of course, they must exist, because if they don't exist, then we won't have that they are the same. Okay, so they must exist, but this is not enough. They must be continuous at AB. Maybe let's even assume that they are continuous on D. These conditions can be somehow relaxed, so you see sometimes different versions of Clause's theorem. But if this is satisfied, then the partial derivatives the mixed partial derivatives at AB will be the same. Okay, so what essentially what you need is, so this is one of the conditions, but you find different versions of this theorem in different textbooks. This theorem, it seems that in the English literature, this is called Clause's theorem, because I know this under another name, sometimes also called Schwarz theorem in Germany, because Schwarz is a German guy. So I guess many different mathematicians have, at the same time, found out this fact, because I know in Russia it has a different name, Russian mathematician. So because this is an elementary fact, and if you do once partial derivatives are defined, you will observe this very quickly. So I guess this was proved. This result was proved by many different authors. So there exist different versions. These are not the strongest condition here, but under these conditions, it can be proved that those two mixed partial derivatives, mixed second partial derivatives, are the same. Actually, the proof is not so complicated. The proof is just the mean value theorem. Maybe let's. The proof is not so easy, but it's a rather tricky application of the mean value theorem. But essentially, directly follows from the mean value theorem. So we define a quantity which will become clear why we define this one, delta H, which is defined as f of A plus delta A B plus delta B minus f of A plus delta A B, and then plus, no, here minus, and then f of A plus delta, f of A B plus delta B minus f of A B. Okay, so we define this quantity here. This function, the function of h, sorry, h does not occur. Sorry, this should be, everything should be h. Otherwise, this doesn't make sense because h does not occur. Now, the h must be small enough such that we are in the disk, okay? Once we are in the disk, okay, because we know that the partial derivatives with respect to x and y and the partial derivative with respect to y and x both exist, they're both continuous. So we can, we introduce, just to make this more clearer, so we introduce this function here, g of, you see this, if you introduce the function g of x, which is equal to f of x, and then b plus h minus f of x b, then you see you can write this this function in terms of g of x as, okay, you have g of and then you have a plus h minus g of a. Okay, now what we do is we use the mean value theorem here, and of course, if we use the mean value theorem, we have to explain why are we allowed to use the mean value theorem. So maybe let's wait. Yeah, here. So let's first, if we use the mean value theorem here. So what we do is we look at the derivative, or the normal derivative, with respect to the coordinates, so call it x, at some point which is between a and a plus h. So let's call this point u, and then times h. This is what you get by the mean value theorem. But you see that what we do here is we differentiate this function with respect to x. But this means here we differentiate this function here. We have the partial derivative here with respect to x and the partial derivative here with respect to x. Okay, so this one is equal to, by definition, okay, so this means because we take the derivative with respect to x of this function, but this is the partial derivative of f with respect to x evaluated at u. So we have here the partial derivative of f with respect to x at u, b plus h, minus, and here the same, the partial derivative of f with respect to x at u, b. Okay. The reason why we are allowed to apply here the mean value theorem, for the mean value theorem, you need that this function is continuous and you need it's differentiable. Okay. This follows from the fact that because we know that the original function f, all the partial derivative with respect to x and the partial derivative with respect to x and y exist and is continuous, and the partial derivative with respect to y and x also exist and is continuous. Because of those assumptions, okay, because you see here, essentially, what you need that this function is differentiable is that the partial derivatives exist. Okay, this of course is true because we know that the second partial derivatives exist. And continuous, the function is continuous because the partial derivative exists. Okay, differentiable function is continuous. So we can use here the mean value theorem. And now here we are going to apply the mean value theorem once more. Now with respect to the coordinate y. And again, because of the assumptions, so what we need is that fxy exists. This is okay. And we need that this function is continuous. This is certainly true because the partial derivative exists. Okay. So here we use again the mean value theorem, and we get this is fxy. So what do we get? A u and another value v, which is between b and b plus h. Okay, times h. So maybe I should write out so the u is between a and a plus h, and the v is between b and b plus h. Okay, so we can write this as f of x y h squared. Okay, so what is the point of doing this? Now, if you look at this relation here, which one to erase? This one. Okay, so the essential thing is this relation here. If you look at this relation here, you can divide everything by h squared and let h tend to 0. Okay, so you have the limit delta h over h squared, h tends to 0. Now you see, so this is we are not sure whether this limit exists, so we have to look at this here. F of x, y, and then you have u and v. But if h tends to 0, you see u tends to a, v tends to b. Okay, and this function is assumed to be continuous at ab. That's why I need that the partial derivatives are continuous. So because we know that this function is continuous, and as h tends to 0, u tends to a, and v tends to b, this will tend to, you can just evaluate it at ab, because continuous. Okay, so why is this helpful? Now I do the same. I just rewrite this. I just do this first in the. So you see here. Here we have for the for this expression we have for the second coordinate b plus h and b, and here b plus h and b. Now we just do the same, but for the first coordinate. So we write this here minus this one plus this here minus this one, and then do the same, but the other way around. Then we get the same expression. We get the same limit, but the only thing which is different is here we get, because we do it in this now in this direction, we get this one. And the limit, if the limit exists, is unique. So those two must be the same. Okay, so you see, the proof is not complicated. The only idea you need is this here. Okay, and then you use the mean value theorem in order to prove this. In order to prove this relation here, you need the mean value theorem twice, and here for this one you need it twice as well. You remember that most of our results follow from the mean value theorem. So the mean value theorem is a very, very important result in mathematics. We also used it last semester several times. For more or less everything we have learned last semester is like based on the mean value theorem. So this is the main tool we have used last semester for proving many, many things. And here the same. So you should realize that the mean value theorem is one of the very essential ideas of calculus and one of the most important results we have learned. Without the mean value theorem, we wouldn't be able to do most of the things we are able to do. Okay, so you see that in most cases, the second partial derivatives, the mixed partial derivatives, will be the same. As I said, this is not always true. Okay, sometimes, because you need assumptions for this, you need that the partial derivatives, the mixed partial derivatives, this one. Of course, to come up with a counterexample, so with a function of two variables, where the mixed partial derivatives are different, because we know that for most of the functions we can write down, it will be the case that the mixed partial derivatives are continuous. Okay, like x, the example you just saw, xy e to the x. Of course, the mixed partial derivatives will be continuous. So if you want to have a counterexample or an example where the conclusion of Clauron's theorem does not hold, of course you have to construct a rather complicated example. So here's one. X to the cube y minus xy to the cube over x squared plus y squared. If xy is not equal to 0 and 0 otherwise. Okay, now let's compute the partial derivatives here. So what I want to compute, what I essentially want to compute is the second mixed partial derivatives at 0, 0. But for this, first I need the first partial derivatives of this guy. Okay, so for the partial derivative with respect to x, now of this function, so I have to, again, I have to divide my consideration into two cases. The first case, or maybe I write this here. So I have two cases. So I have to do it different if xy is equal to 0, 0, and if xy is not equal to 0, 0. If xy is not equal to 0, 0, we can use this expression here. Then we take the partial derivative with respect to x of this expression here. So what do we get? So we have x squared plus y squared square. Now, okay, with respect to x, so we get here 3x squared y minus y to the cube, then times x squared plus y squared. And minus, now with respect to x, so we have here 2x and x to the cube y minus x y to the cube. Okay, so this doesn't look very pleasant. Let's just keep it like this because we actually I'm just interested in the second partial derivative, so we do not really have to simplify it. So we have this 3x squared y minus y to the cube, and then we have x squared plus y squared minus 2x, and then we have x to the cube y minus x y to the cube over x squared plus y squared square. Okay, so this is if x, y is not equal to 0, 0, but we have to do things different for fx 0, 0. Okay, so here we have that y is equal to 0. If y is equal to 0, this function is equal to 0. Okay, and we have this point here. So if y is equal to 0, the function which we have to, where we have to take the derivative at 0 is the function equal to 0, and the derivative of this function is 0. Okay, so okay, so this is the partial derivative with respect to, so actually this is very easy here. So this is the partial derivative with respect to x. Now the partial derivative with respect to y, you get something similar. Okay, so here you have, obviously you have 0, because here you, so this is if xy is equal to 0, 0. So you can first plug in, because it's with respect to y, you can first plug in x is equal to 0. For this case, this is 0, so the function you're considering, if x is equal to 0 is constant 0, so the derivative at 0 will be equal to 0. Okay, so we have 0 here. Now, if xy is not equal to 0, 0, then we have to take this expression here, and we have to take the derivative with respect to y. So we have x to the cube minus 3xy squared times x squared plus y squared minus 2y, and x to the cube y minus xy to the cube over x squared plus y squared squared. Now what we want to have is, so what I really want to have is this one, f x y 0, 0. Okay, so this one is the limit h tends to 0. Now, because the first one is with respect to x, I have to take this one, and then I have f of with respect to x at 0, and then here I have some h minus f of x 0, 0 over h. Okay, so this doesn't look too bad, because you see this one is equal to 0. Now for this one also not too bad, because we can first plug in x is equal to 0. Then this expression, this rather complicated expression, will simplify, because this will be equal to 0, this will be equal to 0. So what is left? So we can first plug in x is equal to 0. Or here we have to plug in x is equal to 0. So we can forget about this expression here. This is 0. So we have minus h to the fifths. And here we have x is equal to 0. So we have h to the fourth. Okay, minus this is 0 over h. You see minus 1. Okay, now okay, so this now how about f of y x 0, 0. So this is now the limit h tends to 0, f of y, and now h 0 minus f with respect to y 0, 0 over h. Okay, so again, but now here we have to plug in y is equal to 0. Okay, so if we plug in y is equal to 0, again, we can drop this one. This is 0, this is 0, so we have h to the 5 over, and here we have h to the 4 minus 0 over h. You see this is equal to 1. So you see, indeed, they are different. Okay, one is minus 1 and one is 1. And this means that this function does not satisfy the assumptions of Laurent's theorem. Okay, now it's you can check which one is it. This one is still continuous, but you can check whether this is continuous. If this is continuous as well, then the partial derivative with respect to x and y is not continuous at 0, 0. And for this, in order to check this, you have to compute here the expressions for fxy and fyx, and you can figure out, okay, is it really continuous? Okay. As far as I remember, this is continuous. This function is continuous everywhere. This function is continuous everywhere. This function is continuous everywhere. But the partial derivatives are not continuous at 0, 0. Okay, you can check it. Okay, I'm not going to do this because this expression already looks quite horrible for me. So I'm not going to compute the partial second derivative. You can do this at home. Okay, so you see that. But the essential thing is what you should learn from this, because actually this is an example which quite often shows up in the Heu-Kau, something like this here, and multiple choice, and then asks you like some properties, and one of them is the partial derivatives. Mixed partial derivatives are the same, and you have to figure out no, they are not. And you see quite a lot of computation to be done for such an example. So if you but now if you see this in the Hoi Kao, okay, because most of the time it's this example. This is a standard example, okay. You know already what is going on. You should, of course, you should also check whether it's really true what I said. Whether this function is really continuous, this function is continuous, and this function is whether the problem really is that the partial. Actually, we know already that this function is continuous at 0, 0 because the derivative exists. No, not really. Not really. This doesn't really mean because this is a partial derivative. Sorry. So the continuous property is as a function of two variables, not just in one direction. Okay. So you still have to check where is the problem in order to use Clauron's theorem. Is it that the original function is not continuous at the point 0, 0, or is it that one of those functions is not continuous at 0, 0, or is it that those two functions, the mixed partial derivatives, are not continuous at 0, 0? Okay, and of course we can also consider higher partial derivatives of functions of 3 and more variables. And again, you have something like Clauron's theorem. So normally, in most of the cases which we encounter, the order in which you do differentiation does not matter. Okay, so this is essentially what Clauron's theorem is saying, unless you have some exotic functions or some functions which do not behave too nicely. Okay, like this one. But in most of the cases, it doesn't make any difference whether you take the derivative first with x and then with y, or first with y and then with respect to x. And the same if you look at higher derivatives. For instance, it doesn't make any difference for most of the examples, for most of the functions, if you first compute the derivative with respect to x and then again with respect to x and then with respect to y, or if you first do it with respect to y and then twice with respect to x, or if you first do it with respect to x, then with respect to y and then with respect to x. Every time you get the same result. And this sometimes can simplify doing computations. Easy example is if you have the function like x to the 1000 and you are asked to find the partial derivative first 500 times with respect to x and then with respect to y, then you should do it first with respect to y and then 500 times with respect to x. Because with respect to y it's already 0, so it remains 0. So this sometimes helps in order to simplify. Clauron's theorem sometimes helps in order to simplify computation. Okay, so we are almost done with section 13.3 in our textbook. The only thing which is left, so there's at the very end there is a very short introduction, very brief introduction to the so-called partial differential equations. This is something which you are, which you certainly will learn in other courses. PDE. Now, the reason why you learn this in other courses is because they are essentially important in physics and in other applied sciences. So, partial differential equations are just equations normally for a function, and they involve normally derivatives of the functions. So, something like a famous example is this one. So, you have this equation here, and you should find all functions of two variables which satisfy such an equation. So the area of partial differential equations is studying these kind of problems. There are not many partial differential equations where we can really solve them. Most of them we can just do numerics, but partial differential equations are of essential. I guess I'm certain you have already encountered them in applications. They are of essential importance in applications. So this one, the Laplace equation, an equation which shows up in very different branches all over physics. And actually, for such a for this one, this partial differential equation has many solutions. It's very easy to come up with one. For instance, this one is obviously a solution because if you compute the second partial derivative of this function both times with respect to x, if you do it for the first time with respect to x, you get y. The second time is 0. And if you compute the partial derivative both times with respect to y, if you do it for the first time, so x is now a constant, then you get x, and then you get 0. So you have 0. So obviously, this function, for instance, satisfies the Laplace equation. But there are many more. Maybe one which is, you can, for instance, check here that this one also satisfies Laplace equation. Also this one, and so on. So many more examples. Sorry, this is one, and many more examples. So it's quite easy to find solutions of this partial differential equation. So this is one of the partial differential equations which is important in applications. Another one is so-called wave equation. This one. This should be x here. And normally we write here a square. So this is the wave equation. And normally whenever you study waveforms, you will encounter this equation here. So for instance, if you look at the string of a violin, so what does this function mean here? So u is a function of two variables. So if you look at the string of a violin, okay, if you pull it up and then release it, so it will go up and down. And you can describe the position, okay, by two. You need two variables. One is time, okay, because depending on the time, okay, the position will be different. And the other one is, okay, what is the distance here, for instance, from this initial point here? So this is your first variable x, and the other one is time. So because with time this will change. And normally the function describing here the movement is given by this partial differential equation. This is the first thing which is always many times derived in physics. And then the question becomes, okay, how to solve it? Normally you have also certain conditions for the function u, which you know from the setting, and you have to find the solution satisfying certain conditions. Now, also for the wave equation, there are many solutions are known here. The most straightforward one, which you would expect from the example I just presented, is like function. So this one, x minus at. And of course, it's easy to check that this function satisfies the wave equation. So we compute the partial derivative first with respect to x, say. Here we have the cosine x minus at. Then we compute the second partial derivative with respect to x. So here we have minus sine x minus at. And we compute the partial derivative with respect to t. So you see here the a goes out. So we have minus a the cosine x minus at. And we compute the second partial derivative. Okay, so another a goes out. So what we have is a square. And then we have a minus from the cosine sine of x minus at. And you see those two just differ by a factor a square. So this function here is a solution of the wave equation. Okay, so this is the only thing I want to mention about partial differential equations, because there is your own theory which discusses how to solve such differential equations either exactly or numerically, and in most of the cases the solution will be numerically. Okay, any questions?